Welcome to our public event today. It's a pleasure for me to have you here. There are two public talks this week, yes, so don't trip them. This one is not from the current trimester program here at HIM, but it's from a workshop taking place at the Hausdorff Center, the Math Center, and it's about queer and trans mathematicians in algebra and representation theory, QTMA-RT. And we do not have public talks during small workshops, but we thought regarding the specific character of this event, it would be a good idea to have a public talk for this. And we are very happy that you agreed with that. And we decided to go here because here is a little more familiar atmosphere than at the Math Center, we think. And we are really happy to have the participants of the trimester program also here in this room. So we have a very big audience. It's great to see. And now it's a pleasure for me to introduce our speaker, Dani Tubbenhauer. Don't be afraid of his name, it's a very German name, but I clicked to your website, and when there's a link, when you click there, how to pronounce your name. And what is said is, it's a magic name, anything goes. so don't be afraid of that. Daniel studied mathematics in Göttingen. Yeah, it still sounds good. Göttingen is still a very important place in Germany, and received their PhD there. And afterwards, they worked as a postdoc in Aarhus, Denmark, and after that here in Bonn at the Hausdorff Center. And this was a moment where we got in contact, I think, because. We had you run a junior trimester program here at the HIM about representation theory, and it was my very first program here in 2017 as a program manager here at HIM. So I'm not being that at the moment anymore, but at the moment I was, and yes, I was very happy with the very high engagement of you, because you answered automatically immediately to all emails. He was so engaged, and I thought it was a standard here, but later I learned it wasn't.
No, my fault.
Yes, after that, okay.
Sorry, can I just request everyone who's seated, can you move to the right, so that people who are...
That would be, that's a good idea, yes, thank you. Okay, and here's an empty. You can also use this one. Yeah, I don't need to place here. I can sit here. So don't be shy. You can come here in the front if you want. Yeah, here's some 3 places. Okay, let's go on then. And then they moved to Switzerland, to the University of Zurich as a lecturer. And in 2021, as a senior research fellow to the University of Sydney. And their current position is ARC Future Fellow. I think ARC is something like the Australian PhD?
Yes.
And looking to the many publications, it's quite difficult to identify the research profile because it's very various. But I would say it's more or less as in your workshop, representation theory and algebra. I hope it's correct.
Yeah, well.
And Dani is also running a very nice YouTube channel about visualizing math. And everyone who loves math should visit this channel. It's really great. There are topics about, some are very elementary, but some are very advanced, and it's very nice to have a look there. So today we'll talk about mathematics, algebra, and AI, or the snake that eats itself. So it's your stage. Thank you very much.
Thank you so much for the kind introduction, Stefan. I indeed identify as an algebra, just to answer your question. Thank you so much for having me. Thank you so much for coming. Yeah, as you said, it's quite difficult to tell what I'm actually doing. So my field, I like to do many things. And quite recently, I got a lot into the question about how can you use AI to advance mathematics. Yeah? And I actually can tell you, we watch a video now together, the starting point where I was like, oh, AI actually can do something for me, because I was always very terrified. But there was this amazing video that you can actually find on YouTube that we just watched together. Hopefully the sounds comes out right. Hopefully the video opens up right.
Hi, my name is Sal Khan. I'm the founder of Khan Academy, and I'm also the author of a new book about artificial intelligence in education called Brave New Words. And OpenAI invited myself and my son Imran here to try out some of their new technology. So we're curious about how good it might be at tutoring someone in math on Khan Academy. So let's get it started.
Very impressive.
It's loading up. See our screen.
Actually, in this format.
Hello there. I'm here with my son, and I'd love you to tutor him on this math problem. But don't give him the answer. You can ask questions and nudge him in the right direction, but I really want to make sure he understands it himself. And he's here in the room, so you can talk to him directly.
Of course, I'd be happy to help. Let's look at the problem together. Can you first identify which sides of the triangle are adjacent and hypotenuse relative to angle alpha?
All right, so I'm pretty sure this is the angle alpha right here, right?
Perfect. That's correct. Now, looking at the triangle, which side do you think is the hypotenuse? Remember the hypotenuse?
I'm not totally sure. I think it might be this one, but I really am not sure. This side AC.
You're close. Actually, side AC is called the adjacent side to the angle alpha. The hypotenuse is the longest side of a right triangle and is directly opposite the right angle. Can you find which one is the hypotenuse?
Oh, yeah, I see. So I think the hypotenuse is this really long side from the. Would that be correct?
Exactly. Well done. Now that you've identified the hypotenuse, can you identify which side is the opposite side to angle alpha?
Okay, well, you told me earlier that this was the adjacent side, and that's the hypotenuse, so I'm guessing that this side, BC, is the opposite side.
Great deduction. That's absolutely correct. Now that you've identified all the sides relative to angle alpha, do you remember the formula for finding the sine of an angle in a right triangle?
Yeah, I know that the sine is equal to the opposite over the hypotenuse.
Perfect. That's absolutely right. Now, can you apply that formula to find sine alpha in the triangle using the lengths of the sides that we've identified?
Okay, so, I mean, you told me that 7, this side BC, is the opposite side. And then you said that the hypotenuse is the longest side, so that would be this side AB, which is 25. So would the answer be 7 over 25?
Excellent work. That's correct. Sine alpha equals 7 over 25. You did a great job identifying the sides and using the sine formula. If you have any more questions, feel free to ask.
Wow. This is wow, right? We go back to the slide. So this, by the way, is 2 years old. So nowadays it can be even better. So it's infinite patience that you sometimes wish your math teacher would have had yet. So I saw this like 2 years ago. It was an old model of ChatGPT who did that actually. And I was like, why don't I use that in my own research, right? So this is like really impressive. And in the end, it looks to me like maybe math tutors will eventually be replaced by AI. We'll see. And so I looked a little bit into how AI can advance mathematics, right? And it turns out it can. It can up to a certain degree, which I'm trying to discuss today. After telling you, with the picture here, after telling you how AI works, essentially what we just saw, how does it work? I will explain it to you. It's pretty simple math, kind of gets very interesting, very simple pieces that get interesting if you stack them together. And I would like to tell you kind of the other side of the story. How can AI advance mathematics, right? It's like a snake that eats itself. How can AI advance mathematics? How can mathematics advance AI? That's kind of the talk for the setup for today. Okay, so I would like to think about the following baby case of what ChatGPT would do. So let's say some kind of the classical problem in AI is like handwritten digit recognition. Yeah. So I'm not quite sure when the post in Germany started to instead of have people just look at whatever the address is on a mail instead of just having it scanned by a computer. But that's essentially what this was about, right? So you want to know digits or whatever letters. And the way it goes, it's kind of very impressive. I have a blueprint for everything AI will ever do for you. Following. Okay? So I would like to see that as a function. I would like to see the idea of identifying handwritten digits as a function. So the first thing I do is I think of my handwritten digit as a grayscale picture. So this is a picture I have in mind. Yeah. So here's my number 3. I really like the grayscale picture. Whatever black is 0, white is 1, and whatever some kind of gray in between. So essentially the whole image, let's say it's 28 by 28, is just a grid of nice numbers here. Yeah? So something like this. So I have an input, right? It's just a 28 by 28 grid of numbers. And what people then do is the following. So you take this grid of numbers, really just 28 by 28, and you just stack it together in one long chain, right? You take the first row, put the second after it, put the third after it, and just do that very easily for you. That's called flattening. So if you have something that's like this, just 1, 2, 3, 4, 5, 6, 7, 8, 9, you just put it row by row, and you get something lower, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. This process is called flattening. You just take this image, flatten it into a long vector. Yeah. Flatten it into a long vector, so I have an input of 28 squared entries from the real numbers, right? 28 squared grayscale values. And my output should be a vector with 10 entries. Why 10? Well, I have my numbers from 0 to 9. I show you what I mean. I want something like that. Yeah? Output should be 0.1, 0 or something. So probability is 0.1 that this is a 0, probability 60% that this is a 3, whatever, something like that. So a 10 entry output vector here. This defines me a function. Literally just a function. So image recognition, and essentially any problem you can think about, is some function on a, I admit, very high dimensional space. Yeah? So 28 times 28 is the input, and in this case, 10 as an output. Right? And then the main question is, essentially we have this function, and we want to understand this function. And this is not a function in the sense, well, you learn it in school. It is a function in the sense you learn it in school, but it's not as easy. You don't write it down like it's a polynomial or it's an exponential function. It's not that easy, right? So essentially, it's very difficult to describe that function. If this would be easy, everything would be easy, right? All of life would be just easy if you could just describe it. Most functions you ever meet in your life, you can't describe it, right? This is one of them, but it is just a function. So the whole idea of AI, underlying all of the AI trend, all of the machine learning trend, is you have a function and you want to approximate that function in a controlled way. Right? The function, we probably can't write it down, but maybe we can approximate it in some nice way. So here's my function. How can I describe a function? Just my task rephrased. I'll go back to that in a second. So what you have in mind is, the picture I have in mind is, that was too much. The picture I have in mind is like this, right? So you have some, in this case you have a nice function. I have some blue function. And what AI should produce is the red function that you see here, okay? And that's our little approximation. Somehow in some sense it's much easier. So what it will essentially do, it will pick certain values. I will make them more precise in a second. It will pick certain values and somehow try to approximate the function in a very similar way as you see it here. Just have in mind that our functions are much more complicated, but essentially that's the idea, right? So AI should be the right thing, an approximation on a function. Your function could be anything, right? You ask ChatGPT a question, it could be that function. What is the correct answer type function? Just formulated in terms of this AI problem. And the whole idea of a neural network is the following. A neural network, that's just the formal terminology that people use here. Yeah. So here is my overview. So AI is this big bubble, but essentially what I'm really interested in, and zooming in a little bit in a second, is what people call machine learning or deep learning. So deep sounds very fancy, I will comment on that in a second, it's not fancy at all. But it tries to answer this type of questions. And the whole point is that it's very different from how you usually used to work with a computer. So most people work with a computer as on the left-hand side. And we give it some very specific instructions, do that calculation, calculate that square root, whatever, save the file or whatever. What I'm doing right now, I'm giving it very specific instructions to zoom into the picture or something. No, in machine learning, that you just give it some data, essentially, and it should figure out everything itself. And I will show you how that goes. I have some nice examples. But it's like really different from the traditional approach, right? So I have this function, and the computer should find the approximation itself. You're not supposed to do anything. The computer is supposed to do it itself. Yeah, it's very, very, very good. Okay, how could we do that? So if you just think, how can I do that? Is there any way to do this? And people were studying this problem for a long time. So the architecture, we will call it an architecture, that you can already see spoiled here on my upcoming slides. The original one, I call it the vanilla network. Vanilla because everyone likes vanilla, the kind of the standard flavor. The more formal name is the perceptron. And people were studying it since the 1950s, 1960s. So that's how long AI actually is already around. I show you some recent more breakthroughs in a second. But essentially what they did, is they have this following picture of I can make that bigger, of a neuron in mind, and this is literally how a neuron works. So this is a neuron. There's some inputs in my neuron, like my picture, and there's some outputs, and then there's something happening in the middle, and that's exactly what I will do as well. So the perceptron, the machine I'm going to show you, literally mimics how the brain is supposed to work. I should say nobody really knows how the brain works, it just mimics it. But that's where the idea came from. And what people will do is the following type of idea. So essentially, it's kind of very, very, very surprising. Essentially, all of AI is just linear algebra. Okay. It's a bunch of matrices, and that's about it. Essentially, my picture on the left, right? A matrix is nothing else than a linear space. So a matrix is just, in this case, it's just a line. A matrix in general is just whatever, a plane, describes a plane or something like this. Just a higher dimensional version of this picture. So here I have a lot of lines, and they're connected, and they have a little bit of a breaking point, but otherwise it's like a linear space. So a neural network is mostly made out of a bunch of matrices. And the numbers in the matrices usually go under the name weights or parameters of the system. We'll see in a second why they're called parameters. And sometimes there's a bias. This is very harmless. I will ignore that for most of the talk, but if you think about the equation of a line is y equals a times x plus b. So that's my line. Like that. This thing here is the b. That's usually what people call the bias, and the matrix describes essentially this piece. The b is just a little shift. You can essentially ignore it, but I will just call it the matrix. So a bunch of numbers, and the main input of a neural network. And then you need some nonlinearities. I will show you in a second what they are. Why do we need nonlinearities? Well, think about the following problem. We want to approximate out a function. It works really well here in the picture upstairs. But if you want to approximate a function like that one, just using linear functions, well, there's not much you can do. You can try something like that. That's what people call the tangent. And that's really good around this little point that I choose. But it's pretty crappy otherwise. Yeah? So essentially what I'm saying is the world is not linear. You shouldn't expect that you can approximate a difficult function using linear functions only. And if the trick people just use is they throw in these little breaking points, these non-linearities, and that's enough to approximate everything. It's kind of very, very exciting or kind of a little bit of shocking. So essentially, I'm going to show you the architecture in a second. All AI is doing, all ChatGPT is doing, and potentially all your brain is doing, it runs a bunch of matrices and see where it gets. Yeah? That's essentially what it's supposed to do. Let me be a bit more precise and then tell you how it works. So yeah, that's what the picture that people usually draw. Not too much, come on. My slides are too large, they don't work very well. So in this case, so this is the picture people usually draw. That's called a neural network. So that describes my approximation the following way. So it's a directed thing, right? So input is on the left, green, output is on the right in red. You're the same, then you cut off. And you can have as many in the middle as you want. They're usually called hidden layers. Input layer, hidden layer, output layer. Hidden is something you don't see, right? You see the input, you see the output. The hidden ones, you don't see them, but they play a crucial role. And how should you read this picture? Well, the picture is the following. At each vertex of the picture, you have one of your values of your input, essentially. So we had a grayscale value. You can think of every vertex representing some number. Right? So you get, in this case, from 1 to 2. And the things in between are the matrices. And we don't know how that goes. It goes as follows. In case you have never seen this one. Blah, 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 blah. Yeah, so we have this little picture here. So I have one little... the first thing is a map from one-dimensional space into three-dimensional space. And you describe it by its 3 weights. As I said, ignore the B. So just the 3 weights, X, Y, Z. And this is just a very boring 3x1 matrix. The other one, whatever, you can do it like the first goes to the first goes to the third, whatever. You just organize it in a matrix, and you have 6 guys, right? You have 6 parameters in your matrix. And that's essentially a neural network. So a neural network is a bunch of those. I'm ignoring the nonlinearities for now, just please stay with me and we'll come back to them. A bunch of those guys together in a big thing. And just to spoil the story, so usually they get very large. Let's have a look at another example here. 3 input, and then you go through a 4-dimensional space, a 3-dimensional space, a 3-dimensional space, and a 2-dimensional space. 3 input, and you go through up to the very end until you have 2 output here. So everything here, so the first one is 3x4 matrix, the next one is 4x3 matrix, a 3x3 matrix, a 3x2 matrix. And the function is just compose all of them, right? So just stick in a vector, this function is just, and it acting on a vector of the input and giving a vector for the output space. Yeah. Okay. So let me come back to here. So that's the neural network itself. So how could it ever learn anything, you might wonder? Essentially, it's just a bunch of matrices, and make this point again. The bunch of matrices stacked after one another. And I should make this point clear that my examples are, of course, very, very tiny. But usually, I have a picture somewhere. Ooh. So usually, you have really large things. So the standard one that uses like ChatGPT, it's called ResNet 152, and it really says it has 152 of those layers in between. So it's really large. The standard image recognition. So if you use your phone, so if you're a more modern phone like me, you can just use your face to unlock it. It's something like a 19 layer type thing. I'm sorry, 20 layer type thing, like in the bottom one. They are really, really large, huge. So that's what you should have in mind. So really large matrices that you multiply together. But how can that learn anything? It's just a really complicated function. That's what I just said, right? With many, many matrices together. How on earth could it ever learn anything? And you do the following trick. It's kind of very, very amazing. You just do what you do with a student. You just let the student give you an answer, correct the student, and ask the question again. Essentially, that's what it is. Yeah? So it does the following. So you want to approximate. There's a mantra. The mantra goes as follows. You have something people call forward. That's easy. That's just, you have a function, you put in an input, you get an output. Then you do what people, so forward. Let's say f. Then you do the loss, I will go back to the second, and then you do the backward, where you adjust the function according to the result you get. The idea is the following, and I have it here nicely on this picture. Oh, that was too much again. Slides are too slow. Okay. I want to approximate blue. I run my function. I get this very bad approximation of blue, right? It's like terrible, really bad. So that's what usually a neural network does at the first place. Essentially, it starts off as random, right? It's just some random function. It does something. Right, fine. So that's how you train students, right? They just give you some really not all that great answer. And then you tell them, oh, by the way, so this is now the loss, right? So I've chosen 3 points to measure just something like the distance, right? So I'm just measuring the distance to what I want. So I already have some data set, and I kind of know the answer. So I train it on something where I know the answer. I let it guess orange. I say, oh, no, not really. You're off here by something. You're off here by something. And you're off here by something. You get a function. It's called the loss function. I'll come back to that in a second. So a loss function. It's a function on a really high dimensional space. Everything here, keep in mind, ChatGPT, very large, 152 layers. I haven't even told you the size of the spaces. It's just really large. But you get this loss function. And what you really want to do, if you look at that picture, you want to minimize the loss function, right? So you want to minimize it. So what you actually do is you get this is kind of really, really exciting. So you get this really large loss function. You should think of it as like, that's very tiny. So here, I have a little bit of a better picture. So let's try that one. Better resolution, yeah, much better. Okay, so loss function is a function in the weights, in my parameters. So you should expect this to be really high dimensional. So picture like that, the loss function is like how far you are away from the truth. And maybe you start somewhere there, right? You're somewhere at the very top. So what do you want to do? You want to minimize the loss. You want to get the best approximation. So you want to go to the minimal point. And there's a standard way of doing this. Hopefully everyone remembers their calculus. Essentially you look at it's called gradient descent. You look at the point where it has the steepest descent and you just follow down the track. Just imagine that this is on a really, really high dimensional space. So here, if this picture would be so tiny, essentially at every step you look where's the steepest descent and just follow that step. It's called gradient descent. It's a very fabulous algorithm, and it will find you one of those little holes somewhere, right? And you just do that. So let me repeat. Yeah, that was quick. What was that? So how does it ever learn something? Well, I think of my matrix entries, yeah, those guys here, as being parameters. That's why they're called parameters sometimes. I feed it in an example where I know the answer. It gives me something. I create the function in the parameters, how far is it off from the truth, and I minimize that function. And I just do that 1,000,005 times. Yeah. Every repeat, every cycle is called an epoch, and you just have trillions and millions of epochs going on. Okay, let me show you then how this works in practice. So the way to do this, just hopefully I have a nice connection here. So there's a TensorFlow playground. It's very nice. Just open it itself. Oh no, yeah, of course I agree. The browser is set to never save anything. That's fine. I don't care for now. Okay, so here's my example how that then goes, right? So here's my input. In this case, I just take the x and y coordinates. You could play yourself, be more fancy. And the output is just presented as a picture. Can I make this nicer? Okay. And then there is this little parameter upstairs. Oh, why am I using my finger? I have a fancy mouse. Which is called the epoch, where we do, well, the process I just described repeatedly. The learning rate, this little thing here, is the step size of my gradient descent. Because you can really imagine, if you do this, and your step size is too large, so you just go in the steepest direction, and you end up somewhere here, because your step size is too large, and then you end somewhere here, and somewhere here, somewhere here, somewhere here, right? But if the step size is too small, you'll never get there, so somehow the learning rate should be somewhere, not too big, not too small, so you can step by step go to the minimum. So the learning rate is essentially just the step size of my gradient descent. And then I can vary here my hidden layers, I can put in something new, whatever, something. And in this case, the problem is, it's a really amazing solution. I have 2 points here, 2 point clouds, a blue one and a purple, what is that color? Orange and an orange one. And I would like the neural network, my AI, to tell me, well, can you distinguish them? Can you kind of separate them? A very simple problem. Can you separate, like your brain is separating them right now into blue and orange. So can you actually do that? And the neural network should learn the solution itself. So let me just run it for you. So it will be very quick. It tries to learn after about 64 epochs, and then it will stabilize. You can see here, this is a loss function that we're trying to minimize. It just drops very nicely. Takes a while to get going. And essentially found the solution your brain found as well. And the point I would like to make here is, just look at the picture. So what did it find? So the problem was to distinguish a circle from a circle, essentially. And it found the kind of the optimal polygon that fits in between. I'm not doing anything, right? It found it itself, just following the process I just described. So essentially it figured out that the best approximation to a circle is a polygon. So old Greek math just rediscovered here in 46 epochs. Very, very impressive. So I thought this was really cool. And before I go to the math problems, and essentially all neural networks work in this way. Sure, ChatGPT is a bit more fancy than this one, but it's the same type of principle. So let's say it again, the weights here, so the entries of the matrices, there are something like 100 on this slide. ChatGPT has, well, they don't tell you, it's company secret, but you should think of them as ChatGPT having like 1 trillion of those parameters to optimize. And the cool upshot here is, you just run that, and then your function is there, right? So after I've trained it for 64 epochs, my function is now done, and I could just use it go and use it in a real-world problem. So the way how ChatGPT works is essentially that, right? They pre-train it on a lot of data, and then they give it to you, and you can use it for other tasks. Yeah. I think that's reasonably clear. But let me now, just to drive that point home, tell you also why you need nonlinearities. So I cheated here and I actually put in a nonlinearity. I will tell you about it in a second again. Because if I just do the linear one, so this is just matrices, okay. So it's supposed to find an approximation of this thing just using linear spaces. And you can make a guess in your head what's going to happen. And just run it. It's not really doing anything. It's essentially trying to, I can let it run, you can see the loss is stabilized. I can't minimize the function. And the problem is, it wants to draw a line to separate those points. It's not going to happen, right? It kind of tries to draw a line in the middle, but it's not really going to happen. And that's the reason why you need those nonlinearities. Kind of an important fact of life is that if you put in nonlinearities, it just does it. Right? So here, I just show you that problem as well, the same problem, right? Different, oh, beautiful. Different setting. Here, you can just, this is something you can separate with a linear function. I'll show you in a second. It's a bit random, I hope that it will find it now. No! Okay, so this is something you can separate. Let's move to that one. This is something you can separate with a linear function. There you go. And it was trying to draw a linear function for the other pictures as well, but of course, it doesn't work, right? In this case, it just doesn't. So the only reason why you need nonlinearities is because you want to be able to approximate everything. And fun fact is that you can approximate everything if you just throw in this little function that people call ReLU. And I'll just show you. So here, that if I use ReLU here, and it was that problem, it was this guy. Beautiful. And the ReLU function is like this ridiculously simple function that all you need. That's it. So it's clearly non-linear, right? It's 0 on the negative values and identity on the positive values. That's all you need. So a neural network, ChatGPT, a bit fancier, but essentially a neural network is you have a matrix, you compose it with that guy. You have another matrix, you compose it with that guy. You have another matrix, you compose it with that guy. And just do that 1,000,005 times. And then you essentially can learn any problem essentially. It's got a very, very exciting. Okay, let me summarize and then let me show you actually how that. So the video we saw in the beginning is just a fancy version of that principle. And I'm always kind of very baffled how beautiful and easy that actually is, right? So, in other words, AI is essentially matrix multiplication and some nonlinearities. Essentially, it's a linear. So essentially, it's the game you learn in school with vectors and planes and matrices. It's kind of very, very mind-blowing. Okay. Let me just show you, just to be completely precise. So ChatGPT is a fancy version of this, and I can tell you exactly what it is. My favorite paper of all time, it's the best name ever, a slogan that I follow. It's called Tension is all you need. So in this paper, they essentially introduce a fancier version of this, which is the underlying breakthrough for ChatGPT. You can see, if I zoom in a little bit, 2017, it's the first version. And then they adjusted, and nowadays AI is just essentially runs on this type of architecture. So it's a really amazing paper. And so it's my favorite name ever. So I'm clearly a big fan of that name, in case you haven't noticed that. Right, so the machinery is out there for a while. There have been breakthroughs along the way. I haven't told you about computational complexity. You have very large matrices that you need to multiply. But essentially the machinery is out there. So why on earth don't we use that in mathematics? Right? So why on earth don't we do that? That was kind of the question I had in mind. So let me tell you what we can actually do. So it turns out that, slides are too big, that in science, AI has done, so in science in general, like think biology, chemistry, something, medicine, AI has done up to this point, like a lot for you. just it's ridiculous what it can do. One of the major open breakthroughs was kind of the predicted protein folding. I mean, if you don't know what it is, it doesn't play a role here. But essentially, every longer molecule has a certain secondary, tertiary, quaternary structures because it's now very long. So it kind of folds and knots itself, and you want to predict that, and that plays a huge role in how proteins work in your body. It was a huge open problem, and they trained a neural network to essentially detect the properties a protein will have from a picture of the fold. Okay, so very impressive, many impressive results in biology or whatever. Yeah, this is one example. So if you know that, and from drug discovery to climate models, climate models. So if you know that, you're wondering what's the mathematics, right? So if it can do all of these fancy things, like it can teach a student how to find whatever the cosine of an angle, which I can't do, but I can. So why is it not happening? And I think one of the main problems, and that's some kind of a slogan you need to have in mind. So if you just later you're bored, like me, and you just take your first favorite research question and put it in ChatGPT. So I tried earlier like yesterday, two days ago, I was trying to prove one of my theorems using ChatGPT. And it kind of works, but it's really like more talking to a kid. Like you give it every next step and eventually it will get there. And the real reason why this is happening is you should think of the difference between a computer, a laptop, and a compass. Right? So general AI, like ChatGPT and friends, the big ones, they are okay for most tasks. So if you have a more yesterday, well, this actually really happened yesterday. Some people here probably can confirm. So my flight got delayed. I was coming here from Manchester. What a surprise, the flight gets delayed. So they usually tell you the stupid information, like your flight is delayed by X minutes, and having a little bit of experience traveling, if they tell you X minutes, it's clearly not X, it will be something larger than X. So I did this fun trick and just told ChatGPT, oh, here's my flight number. They say it's delayed by 30 minutes. How much will I be really delayed? and it did something really smart. So it looked up the flight number. Cool. The only information available is what I had as well. It will be delayed by 30 minutes. But then it did something smart. Instead of looking at the flight number, which is kind of sticked to it's my flight, right? It's my flight. It looked at the airplane number and looked up where the airplane is at the moment. And turns out that the reason why I'm delayed is because the incoming airplane, which will change to my airplane, is delayed. Okay? That's what it figured out itself by just searching the web. And then it did something very smart. Then it says, okay, that's the information you got. This airplane is delayed by 30 minutes. So your flight is at least delayed by 30 minutes. And then it took the history, which you can easily find online, from those flights, averaged over the various delay times, and gave me an approximation on my delay, which it said it would be 1 hour instead of 30 minutes. And it was essentially 1 hour in the end. Very, very smart. It's very good for those tasks, right? It's a general AI. It has learned, someone had this trick somewhere to look up the airplane instead of the flight number, and then average. You learned it somewhere, it picked it up, it just gathered the information, done. If you really think about a research mathematician, that's more like the opposite. Yeah? A research mathematician is more like a compass. It can do one thing, right? It points to north. Can't do anything else, essentially. So, research tasks should be mostly like for specialized AI, at least at this stage, right? So if you ask your favorite research question to ChatGPT, it really likes to have data given to it, someone wrote it, then it spit out the answer. So if you're asking for a solution to an exam somewhere, and it's like a very classical topic, it will find the answer. But if you really have a research question, it usually gets pretty stuck. Okay, so you should have in mind that most of machine learning for science or math is on specialized AI. We have one model that can do one thing, and nothing else. So let me tell you what is actually known at this point. So what people can do. It's very impressive on the one hand, and it's very unimpressive on the other hand. So I probably still have my job in 5 years or so, but I probably don't have my job in 50 years. So crazy that you know what I mean. It's pretty impressive what it can do already, keeping in mind that the human brain is like 1 million years in development. I'm not a biologist, it's probably more, I have no idea. And AI started like 100 years ago, let's say. It's pretty impressive. So let me show you one of the, so this is the underlying problem, and this is one of the key problems right now in AI. How can you teach AI to do mathematics? Because essentially math is the art of reasoning. Yeah? So people trying to see, where does it come up, right? Mathematics, the art of reasoning. How can we teach AI to reason? Then again, my example was a flight. It looks like ChatGPT was reasoning, but essentially it just found the solution somewhere and copied it. So, in that sense, it was maybe not real reasoning. Okay, let me show you one example. The most impressive one up to date, in my opinion. So how can it be used in algebra? In particular, in matrix multiplication. So it makes matrix multiplication faster, so in particular it feeds itself. Right? Essentially, the whole complexity of the problem is to compute matrix multiplication, and it found a way to make matrix multiplication faster, so it feeds itself, like the snake that eats its own tail. That's what I have in mind, right? So alpha tensor is the name. It's one of those specialized guys, right? Don't worry too much about what it is. And deep learning, so it's a tool of deep learning. I haven't said that, but deep learning always scared me a lot, the name. But it really just means you have a lot of layers, right? It's more like long instead of deep. I'm not sure why they call it deep, but just to scare people, right? Deep learning. very, very mystical. No, it's just you have a lot of them. It's deep in the surface. And I will describe now that it found new algorithms to speed up matrix multiplication. It's like very impressive. And the way they did this is the following. So here's matrix multiplication of a 2 by 2 matrix. A times B, whatever. And you see on the top right, let's do the count. Oops, that was too much. There are 8 multiplications, no other additions, there are 8 multiplications, right? A times E, B times G, A times F, B times H, C times E, D times G, C times F, D times H. 8. That's what you would expect. And then there was a German mathematician in the 1960s, Volker Strassen, who just said, no. We only need 7 multiplications. And here they are, it's ridiculous how they look like, quite complicated. But you only need 7 multiplications in matrix multiplications, right? So the only thing you need to know at this point, 8 is the standard, 7 is of course better than 8, that's not difficult, and it's quite difficult to find the 7, right? It's not something you just write down because you're bored. Of course, as soon as you have the solution, you can easily check that it works. But to get the solution is a non-trivial task. And you might wonder, why does it make my matrix multiplication faster? I mean, I saved one operation. Come on, you saved one operation. 7 instead of 8. Well, the idea is the following. And it makes it much faster. I have a nice picture here. It makes it much faster because of the following. Essentially, the idea is now to apply it. It's called divide and conquer. Okay, we have a 2 by 2 matrix. But nobody ever said that our entries are numbers. They could be matrices. Right? So you're thinking now of a large matrix and another large matrix. You divide it into a 2 by 2 thing, and you save one operation in multiplication on those large matrices. And you have 7 operations in large matrices. Well, now do the same again for the next operation. You divide it again into a smaller problem. You save one operation in each of the operations. And keep on going, right? And this doesn't sound very impressive, but if I show you the picture, I have a better zoom version, it's actually really much faster. Okay. So instead of having a cube now, I just have a square to make it easier. So let's say you have 4 operations. 2 times 2 is just a square. And let's say you save 1 operation, well, you have 3. We'll poke out the little corner of the square. But now you do that in every step, and this is a large picture. So it really will look like that, actually, right? So in every of the black boxes, I save 1 operation. And in every of the little black boxes, I save 1 operation. And I save 1 operation, and I save 1 operation. And eventually, it thins out a lot. Right? It's not nearly a square anymore. That's why people got really excited about saving 1 operation. You just do it iteratively, recursively, and you get a much faster algorithm to multiply matrices. The formal way to measure that, in case you wonder, is that was too much. Yeah. So the standard one is n cubed operations. You had 8, 4, 2 by 2 matrix, and this faster one, you save in the exponent. That's why it gets so much faster. It's now log 2.7, right? Instead of log 2.8, which is 3. Log 2.7. Yeah. So people got very excited about trying to get this number as low as possible. It's matrix multiplication, right? You want to get that number as low as possible. But from the picture, it's like absolutely not clear how we would do that. So now you would think of, well, with some more work, you can show that this is the only solution for 2 by 2 matrices. So you would like to look for patterns for maybe now 3 by 3 matrices, or 4 by 4 matrices, or 5 by 5 matrices, and you want to save operations on those, right? So you need to somehow find some pattern of how to arrange the matrices, like in this bit here, such that you save an operation. It's absolutely not clear how we would do that. It's an open problem in the field, was an open problem in the field for a long time. How can you speed up matrix multiplication? And they trained a neural network, which actually was very successful. I just show you the result, and then I show you the relations that you don't want to know. It's already here, you see that. But they found a 5 by 5 example with 76 operations. So 5 by 5 should be 5 cubed, should be 125 operations. So they saved quite a bit of operations. So this is called alpha tensor. It's kind of a lot of fun. They have all the relations on their website. So this is Google, and they just list the matrix multiplication 555, and they just list all the operations here. Yeah, I have no idea how this network ever found this. But yeah, 76 instead of 125. So it's very, very impressive. To get down to something like 2.69 as an exponent, right? Log 5. And this is really much, much faster. Right? It's in the exponent, so every point you save is just exponential in this case. This was really impressive. So that's what AI can do for you already. So people tried that for a long time. And the story goes as follows. People tried that, and there's no way you ever find that, right? So AI did that, but secondly, people were still a bit smarter than AI. So here's my little graph. Hopefully I get this one zoomed in. So the omega is the exponent, so omega is really just the n to the omega. People call it an omega. You get the exponent. Here's my little Strassen, first drop, and this is just the time axis. So people tried, so Strassen and some other people. And this is where they ended. And we were at 2.6, so alpha tensor is like here. And then people were a little bit still smarter than AI, because they realized that this method is not getting us anywhere, it gets too complicated. And they came up with a different method. So everything below here is, if you know what it is, the fast Fourier transform. If you don't know what it is, that's fine. So just a different method, right? So right now, this is exactly how AI works in mathematics. It can reproduce results and potentially improve on results, but it's still not quite on research level, if you get that, right? So it somehow stopped here in the 1980s, roughly, where people were still developing new methods. And this is literally what AI does nowadays. I have some examples for you. I just want to pull one of them up one of them. So what I think is really cool and really well working right now is the following. So mathematics is all about proofs. Writing automated proofs is not that great, but the following works really well. Write your proof, and you want to computer verify it. So you need to write it in computer verifiable language. So you need to translate it to computer verifiable language. I'm in the first point now. And that's a pain in the neck, because how humans write and how computers write is very different. But if you just ask ChatGPT to translate for you, it's almost perfect. So that's something it can do very well. Right? So they train now a specialized network that can take human written proofs, translate them in computer verifiable proofs, and then just verify that the proof is correct, which is very impressive. So essentially you take a picture of your phone with your handwritten proof, you translate it into formal symbolism, and yeah, it will solve it for you. It's very impressive. There are other really nice things it can do in algebra, for example. I'm almost done, don't worry. So it can pick out groups from Latin squares. So if you think about a Latin square, it's very simple. Latin square is just exactly the pattern you see here. You have 4 colors in a 4x4 square, and every row and every column contains exactly one color. And that's almost what mathematicians call a group. What mathematicians call a group has another law. It's associativity of the multiplication, which you can't really see in that table, but they trained AI on really large Latin squares to find the groups inside of the Latin squares. Very impressive work. They even can find the simple groups in the Latin squares. It's ridiculous. So some things are really, really working very well, but essentially, the thing I would like to end with is, so it's really growing, and I would like to promote this idea of having a look into it. Not quite yet popular with the usual mathematicians. Yeah, and I kind of feel like the real reason is, if you really look at what most of these networks are doing, they still use the perceptron. So in this case, as a mathematician, you always feel like all the other sciences are running behind you. They just use math ideas from the God knows when. In this case, I think it's the opposite. We are very far behind from the latest models, and running some large language model like ChatGPT on a real math problem is still out there, and I would like to end with this. Things that I learned, things that I didn't. Somehow, maybe I feel, maybe it's just me, but maybe I feel we somehow learned the wrong things in school or in university, right? So I learned that this function is not differentiable, but nobody ever told me how a neural network works or how a computer works. Okay, thank you so much.